So we're last class was optimization problems. Now this is optimization problems with specifics to economics. So max, min, profits, revenue, all that kind of stuff. Some of these examples actually I think we did touch on a little bit. I think it's kind of the day that we kind of stopped because you guys didn't know what a lot of those things were. Now we kind of know what they're asking, what they're telling us to do, so we can work a little bit, move forward now. So when average cost is a minimum, then the marginal cost is equal to the average cost. So what that means is if it asks you to find a minimum, you would set the average cost equal to the marginal cost. If it's asking for a minimum, like if you're trying to minimize the cost of a product or whatnot, okay? Now, what I want you to understand is whenever it says marginal, think about instantaneous cost, okay? So when I say instantaneous, what do you think? Do you think derivative, okay? So whenever you see marginal cost, marginal revenue, marginal, I think that's the only two, but yeah, but whenever you see marginal, you think derivative, okay? So let's just look at this first example here. Let's kind of work through it. Now, an important page to reference in your notes is that page that has all these listed what they are. Okay, I'd be honest with you, I don't have them memorized either. Like revenue is X times P, which is P stands for demand. Okay, that's the revenue equation type of thing. No, you do, but I'm saying use your book to reference those. Like I'm not going to make you memorize those. You should get those. You won't? Yeah, we'll discuss that later then, because I don't think there's a reason. There's not a reason to have you memorize that, so I'll see if I can figure something out for that. Okay. All right. So the cost in dollars of producing X 5-kilogram bags of flour is. So this is the cost equation for producing the flour. Okay. Big C. Okay. What I do is the book uses big C for cost and then little c for average cost. I just put AC next to mine. You can do that if you want because little c, big C looks the same. Anyways, it wants us to find the average cost and marginal cost when producing 100,000 bags of flour. Okay, so to do the average cost is, so I'm going to call it AC. Average cost is equivalent to cost over how many you're producing. So just over X. And we're just going to leave it as X for right now. And so what that is that you're going to pretty much divide this whole thing by X. So what I like to do here, I simply like to just put it, I do it separately. So I like to go like this over X. That X cancels, so I just call it plus 0.43. And then that is now going to be plus 0.00001, 2, 3, 4, 5, 2, 3, 4, 5, 1x, because the x squared cancels with an x. So what I did was I took the cost equation, I divided it by x to every piece. X, that canceled. X squared is now an x. So I divided x to my whole cost equation. So this is your average cost equation now. This is because that's what we define average cost to be. This is the definition of average cost is cost divided by x, which makes sense. You know, you have a price of price of 10 desks. I would divide the cost equation of it divided by 10 because I have 10 desks and figure how much they cost a piece. Okay. So what we're going to do now is just simply all we have to do is for this we would just put in 1,000, or excuse me, 100,000, right? Yeah, 100,000. Okay, so we put 100,000 in for x's here. When you do that for that problem, that's just calculator work, so I'm not going to go through that very closely, but it just kicks out $1.93, which stands for $1.93 a bag. So the average cost of making flour when you have 100,000 bags produced is $1.93 per bag. Yeah. Any questions with that? Okay. So then, when we do marginal cost, we do what? We take the cost equation and do the derivative of it. Remember, marginal, think derivative. So marginal, you can do M or you can call it C prime, whichever you want. But if you remember, M stands for the derivative, that's gone. That's just 0.43. That's going to be 0.0002x. 1, 2, 3, 4, 5, x. Whoops. Okay. All these garbage cans came around. I don't know where they're from. I don't know why they're all here now. Okay, so then we're going to put 100,000 into it. Kind of like that one, though. What is That's the derivative of the cost equation. So this is the same thing as C prime of x. Marginal derivative. Okay, now we plug in the 100,000 again, and then for marginal, we are going to get 63 cents per bag. Whoops.
And marginal cost is that thing that we were super confused about.
Right, marginal is like, it's really hard to explain. Marginal is like when if the more things you sell, the cheaper you can make it, right? The more things you can sell, the cheaper you can make it, so the lower your price, and you want to maximize the profit, whatever, right? Yeah. So the marginal is that different instance for that bag of what the price change is, like what it's slope at that point. Okay. And so it's like our tangent slope, because it's derivative, so it's still a tangent slope, and then we did it at 100,000 bags. Okay, at what production level will the average cost be smaller, and what is the average cost? So for this one, that means smaller, we should think minimum. Okay, we're looking for smallest, so this right here makes us think we're talking about a min. And then the directions at the top, we're looking for a min, marginal cost equals average cost. We're looking for a min, marginal cost equals average cost. Okay, so then what we're going to do is we're just going to set them equal to each other. The two equations here. This equal to this guy. So let's see if I have some room to write this out here. So 140,000 over x plus 0.43 plus 0.023451x equals 0.43 plus 0.0002x. Okay, so I set them equal to each other. Okay, and then we can just solve. So when we solve, if I move the 0.43, you'll see they'll cancel. I can subtract this over to here. Just solving is all I'm doing for x. And I'll show you why. I like to get this by itself, and I'll show you why here after this next step. So 0.0002x minus 0.001x is just 0.001x. Okay, and then what do you think I'm going to do now? Yeah, multiply both sides by x so I can get rid of that fraction. And then now, all you have to do to solve is, and I'll just kind of, you guys can do this in my room, you divide the 0.01 and then square root. That's our last two steps. So I divide this big decimal here. Yep. Okay, and when you square root, you're going to get 374,165 and 73 cents or whatever. Oh, this divide? Yeah, it's a big number. It was 1.4 e to the 11. So 1.4 with 10 zeros. And then we square root that, and it's 374,000. Okay, and so then it says, but at what production level will the average cost be smaller, and what is the average cost? So this is the level. So we plug this in, and it'll give us how much a bag, right? The X is the level of like production, and so then the Y is our like output for money. So when you plug this in, you can put it right back into the cost equation, and so just like it's a point, right? So we just figured out that's the X value, 374,165, and then 70. What do I have? 73. And then the Y value of the outputs, just so you know, is $1.18. So that means $1.18 is the minimum cost that we can have for our flour bags, and it's at this production level.
What do you mean by production?
How many bags?
Oh, okay. So when you're making that many bags, that's cost per bag.
Yeah, and that's the minimum cost.
Okay.
So that would maximize our profit most likely, right? Minimize cost, maximize profit. Yeah, so it's this one. It's the minimum down here. Because it's like a really, like technically this is a parabola. On your calculator, it's going to be a very, very big guy because it's really big numbers. So he's going to be very flat looking. Yep. Anything else on that one? Okay, and we just have two more examples here. Okay, so the next page then, if there's no questions. So going back to that hamburger type problem that we were doing, I think we did one yesterday. The cost of Sarah's hamburgers with a yearly demand function. So demand, they use P, little p, is 80,000 minus X over 200,000. 800,000 minus X over 200,000, sorry. And the cost function of 125,000 plus and this is 0.42. So put that, there's not a misprint there in your notes, 0.42. What level of sales will maximize the profit? So now we're trying to find the max here. We're trying to maximize profit. So also when you're thinking about min and max, we still think derivative, but we need the profit. We don't have a profit equation, so how do we get a profit equation? Okay, or if you read I think there's also the second line, but let's write this down. Profits are maxed when marginal revenue equals marginal cost. That makes sense because that's when they equal each other, that means that they share that slope at that given time, which matches them up in terms of our not philosophy, but in terms of our idea of them equaling each other. Okay, so real quick, revenue, just so we remember, and I said it before, is demand times X. So X times P. So this function times X stands for revenue. So then our revenue equation, R of X is 800,000 X minus X squared all over 200,000. That's our revenue equation. And just quickly here, I'm going to go ahead and divide that 200,000 because I can. So this piece turns into 4x. 800,000 divided by 200,000 is 4x. And then it's going to be, this just stays the way it is. Yeah, x squared over 200,000. Just helps me because I have to take the derivative. I'm looking for marginal revenue, right? So I just said, I'm trying to get marginal revenue right here. And then we can get marginal cost from this guy here. So that's what I'm working towards right now. I'm working towards getting marginal revenue, and then I'm going to do marginal cost. And set them equal to each other because that is a way we can max out our profits. Okay, all right, so this derivative, R prime, so revenue prime, or marginal revenue, is 4 minus x over 100,000. See how I got that? Drop the 2 over 200,000 reduces to 1 over 100,000. Took the derivative of each piece there. Okay, 4x turned to 4. Drop the 2. 2 over 200,000 is 1 over 100,000. So that's right there. That's your marginal revenue.
Why wouldn't you do,
Quotient?
yeah.
Because there's not x's. There's a constant on the bottom. Because if you could do quotient rule, but it'd be tedious. Because what's the derivative of low? Right? You only do it when there's variables. Okay? All right. So now I want to do marginal cost. Marginal cost, really simple. That's 0.42. It's that simple, guys. 0.42. That's your marginal cost. So we set them equal to each other now. Marginal cost equals marginal revenue equals, will tell us your max profit. So here we go. So 4 minus x over 100,000 equals 0.42. Again, I like to isolate my fraction so I can multiply that bottom off. So the first thing I do is I'm going to subtract 4 here. So then I get negative x over 100,000 equals 0.42 minus 4 is negative 3.58. And now I'm going to times by a negative 100,000 to get rid of the negative and to get rid of the 100,000. Have x by itself. Okay, so right here, I'll write it. Times. So you get 358,000 hamburgers will maximize profits. 358,000 hamburgers, so obviously hope that's a chain, not one restaurant, but okay. 358,000 hamburgers will maximize their profit. It just says what level, so that is the level, so we don't have to. But if you plug that in, it would tell you the profit. Well, what are you asking? What are you trying to find? There's no. What's your question?
Okay, well, I get it now. Like, if you're trying to find the cost.
If you're trying to find how much it costs you to make that, you put into cost. If you're trying to figure out how much it makes you, you put into profit.
Yep.
Okay. Yep. Very good. Anything else for you? The last one. Got a baseball one in here for Garvey. Keep him, keep his brain going. All right. Okay, so a baseball team plays in a stadium that holds 52,000 spectators. The average attendance at a game was 27,000 with tickets priced at $10. When ticket prices were lowered to $8, the average attendance rose to 33,000. Find the demand function assuming it's linear. Okay, so they're saying the demand function is linear. So guys, help me out here. What would you try if you're given this on a test to figure out your demand function? They're telling me it's linear. Okay, so if I think linear, I think about my x and my y's, my change, my rate of change. So how could I figure out something through that information that could establish my rate of change for my spectators and ticket prices? Huh? Rate of change, that's slope. That's y equals mx plus b, linear. Huh? So, okay, let's take a step back further. Go to the basics for you guys here, maybe a little bit. So what is, in this situation, what represents your x value? Price per ticket or people that show up? Which one is independent? Price is independent. So my x is ticket prices. My y is people or population, whatever, spectators that come. That's my x and my y. Something good to establish here. So you guys are making me sad, but what you're going to do is understand that these are like points. $10 gets you 27,000 people. You have to do slope formula first, but yes, we're trying to get y equals mx plus b. It's like 2 points. $10 gives you 27,000 people. $8 gives you 33,000 people. Okay, so then we're going to do slope form. Remember, y minus y, x minus x, all that old good stuff. That's how you find slope. That's slope formula. Okay, So I'm going to go 27,000 minus 33,000 over 10 minus 8. That gives me negative 6,000 over 2, which gives me negative 3,000 is my slope or my rate of change. So essentially what that means is for every dollar I raise the price, I lose 3,000 people, which makes total sense, right? If you raise the prices, you're going to lose people. Okay? So this is where we're at. Like Rachel was saying, we want the mx plus b. We're just missing the what now? The b. So we want to figure out what the start was for this equation. Now the start might not be reasonable, but it's because the line, there's a starting point. Like, you know how you have graphs that even though you can have negative time, they still look like they're going to go there? Same type of thing. What I'm telling you is, well, I'll get the answer first, and then I'll tell you why it doesn't make sense. Okay, so how can I figure out b? Plug a point in. Any point, any spot, okay? So I'll just take the 10 and 27,000. So I put 27,000 here for y, because it's the y value. Negative 3,000 times 10 plus b. Okay. Negative 3,000 times 10 is negative 30,000. I just add that over now. So b is 57,000. So why does that not make complete sense? Right. Stadium can't hold that many. Stadium only holds 5,200. It's saying 57,000, but I think it's kind of an assumption that what would have to happen to have 57,000 people? I guess it could happen. It'd have to be free. So maybe it's standing remotely, maybe that place is just packed because it's free. If you want to think about it that way. But the reason I'm saying is because there's the spectator limit is 5,200 or 52,000. So, anyways, this right here is our demand function. Okay. How should owners set ticket prices to maximize revenue? Okay, so we want to maximize revenue. So we need to get a revenue equation and take the derivative of it. How do you find revenue again? It's demand times X, right? Revenue is X times P. Okay, P stands for demand. So all we're doing is taking the one we got and timesing it by X. So our revenue equation is negative 3,000 X squared plus 57,000 X. But we want to maximize that, so we want to find the max using our skills of derivatives. So we're just going to go ahead and take the derivative right now, and we are going to go, R prime is negative 6,000, so I drop the 2, and that just loses an X is all. Okay, get that down. I'll let you breathe for a second. We're just finishing this thing up. We're almost done. Let's go back to Unit 3. Let's go back to all the hard work you guys did for that long unit there. What do I want to do here to figure out the max? So we take the derivative and we set it equal to what? We set it equal to 0, right? Because 0 is the zero slope line of the maximum. Okay, so we just pretend this is 0. And now we solve for x. So minus the 57,000 and divide the negative 6,000. When you do that, you're going to get your maxes at $9.50, which stands for $9.50. So to maximize our people, we'd want to charge actually between the $8 and $10. We want to charge $9.50. Okay. All right, and that's it for this lesson today.